So I have added a link on the schedule to a midterm page that first off has some practice exams. But these are old exams that I've given in the past. Some of the topics that are covered are different, and the operating system that is used is different too. But you'll get a flavor of what it's like, and some of the questions are perfectly relevant to you. But you may find as much as half of the exams like, what's this? You know, or we haven't covered that. That's okay. All right. What's that?
Half of it's going to be what is.
So we have 4 practice midterms. Half of them, you will look and you'll say, we have not covered this. And so you'll say, I'm not going to look at this then. Okay?
But that's not going to happen on the real one.
We could take for a vote, if you want, as to whether people want that. But no, of the practice midterms, only half of it will be relevant and be on the real midterm. And I'm saying roughly half. So there's topics that are covered that we didn't cover on the midterms. And vice versa. There's probably stuff that is not in the practice midterms that will be on our midterm. Okay? So you can use, and I have a correction here that I'll make right after class. So you can use the books from this class. You can use the XV6 book. You can use the 3 operating systems in 3 easy pieces book. You can use the notes from class that you want, or any notes that you've taken. So you are not going to need any of that, assuming you study well. So it's not going to have stuff that you're going to be required to go to those books for. But you may use them if you want. And you can bring a laptop and use the course website, you know, the references, the Intel stuff, the copies of the slides if you don't have them, what else? And you can also use your GitHub repository for JOS. Okay? Does that make sense? So it's basically the class website, anything you can get to with one click from the class website, you know, that it directly links from to, and then your GitHub JOS repository. Yes?
Will the answers for the practice test be posted?
I think they all include, several of them include solutions. There are 4 of them, maybe all of them include solutions. All right? And if you don't want to bring a laptop, you can also take the exam down in the B105 lab if you want to use the computers down there. So if so, just come a little early to pick up the exam. Any questions? Okay. So it covers through this Wednesday's lecture. There's something that I had never gotten to on a previous lecture that I wanted to get to, and that's something about JOS. And that is the UVPT, so the user virtual page table, which is at EF40000. So the idea is, so we're going to just kind of keep that number in mind for a second. We have got a bunch of page tables, right, that are non-contiguous. Right? Because when we got our page directory, it points to this page table and this page table and this page table, and they're all over the place. Wouldn't it be nice if we had some way of making them appear to be adjacent to one another in the right order, so that you could just treat it as a contiguous array of memory to get any particular page table entry? And basically what happens is we use a sort of a trick of the paging hardware to do that. So but let me just sort of show you what I mean. So we've got our page directory here, and we are pointing to a bunch of different page tables here, right? That one may be there, and this one may be here. So this is page table 1, page table 2, page table 3. And what we'd like is these to appear in memory, in virtual memory, as contiguous. Because if they were contiguous, it'd be really easy to get to any one of them. Because you remember your page-dir walk and how, I mean, it was a little complicated. You had to write some code to do that. But if you had an array of page tables that were all directly in order, if you wanted to get to one particular item, you could just directly go there. It'd be easier. So here's what's done. Let's look at what the MMU does. Right, so the MMU uses the CR3 register, which refers to the page directory. It's a physical address or virtual address? Physical, because if it were virtual, we would have an endless recursion. And then we find the page table by taking the page dir, taking the page directory index, right, the top 10 bits, multiplying by 4, indirecting. That gives us the page table, and then we get the page. We basically do that again with the page table index as opposed to page directory index. Okay? So nothing complicated about that. What is interesting, though, is it's just dereferencing pointers. Okay? So if we set things up such that, right, so here's our page directory, here's our page table, it's going all over the place like this. If we set an entry in our page directory that points at the page directory, interesting things can happen. Okay? So here's what we're going to do. We're going to take 3BD. Now, why 3BD? That is the 3BD entry in here. Okay, so 0, 1, 2, 3BD is towards the end, actually, but this entry. Why 3BD? Because EF400, the top 10 bits of EF4, 1, 2, 3, 4, 5 is equal to 3BD. So therefore, this is the address within, so we're going to use an address that looks like this. 3BD followed by, let's say, 3BD followed by a 12-bit offset. And this is not quite right because 3BD, you don't just concatenate them together, right? Because 3BD is only 10 bits, and so, but it's the right bits in there. 3BD in the top 10 bits, 3BD in the next 10 bits, and then an offset. Let's see what happens. All right, so this is, in fact, what UVPD is set to. Okay. That is EF40000. So we take the CR3 register. We indirect into here 3BD in. Okay? And then we have set in this page directory that this points back to itself. So when it goes to find the page table, it ends up here. Here's the page table. This is the page directory, and it's also the page table. And now we say, okay, go in and access 3BD again. Okay, we go to 3BD, we dereference it, and where we go to? We loop again back to the page directory. So this is saying the page is, the page table is the page directory. That part's not very useful, okay? But true. Where it gets to be interesting is if you use something other than 3BD as the page table index. So use 3BD as the page directory index. And then you do, for instance, 1. Okay? So we're going to look at this address here. So this is let's just start here. So what's going to happen? We're going to go through, we're going to go to 3BD, we're going to indirect, which takes us back here, and then we're going to go to 1. And that'll give us the address of what we think of as our page, which is this page table. So if we use 0, we'll get to this page table. 1, we'll get to this page table. 2, we'll get to this page table. And so every page, every one of these page tables ends up in order, adjacent in memory.
Sorry,
True.
what's the relevance of the 4 everywhere?
Because pointers are 4 big. right? So the size of a PTE or a PDE is 4. Okay. So the quick description of this really is your page directory can point back to your page directory, and then that allows you to shortcut and go, instead of, call this 1, 2, 3 deep, we only end up 1, 2, or 1, 1, 2 deep.
So if this is mapped for user space, then do we have to worry about the permissions in the page directory not being set properly for the page tables, and the user base either being able to mess with them or not being able to see things we'd like it to see?
What we do is we make them read-only, so we're not going to allow the user process to actually write them,
But if
I
you
believe.
make them read-only, then doesn't that mean that the pages that they're actually mapping are read-only? Or where are
So-
you setting it read-only? Just because this information is used twice, both in like mapping it, but then also
Yeah.
in the actual.
So we're going to set the, let's see, the user readable in this page directory entry.
Okay.
And then these can be readable or writable, it doesn't matter, right? So that these pages are readable or writable by the user. But the page table is only readable by the user. Page tables, I should say. So once you've done this, you could rewrite walk pagedir if you wanted to just go use this in JAWS.
You also need like a kernel virtual page directory, kernel virtual page table. You want to do that?
Not read-only?
Because we marked it readable.
Oh, yeah, given that we would want the kernel to be able to change, yes. All right. On Friday, we had looked at thread cleanup and the fact that we mark these threads as killed. We check at various points in the kernel. When we start a syscall or when we end a syscall, if there's a bad page fault, then we will go ahead and mark the process as killed. And we also talked about the fact that we need to wake up our parent, and if we have any children that are waiting for us, then we go ahead and reparent them. Okay? Because since we're not here anymore, we're not going to be able to wait for them. When we reparent, it's always the init proc. So the init proc is the very first procedure, right? So this is the init proc. And it does forking, and those can do forking, and these can do forking, right? And this may fork, and this may fork down here. And let's say this guy gets exited. Then its child, who this guy hasn't waited for, now becomes a child of not its grandparent, but back to Adam, right? The very first. And that guy's job, init proc, is only to wait for children. All right, so what do we do if a target is sleeping? So somehow we've decided we want to kill this process, but it's sleeping. It could be waiting. It could be waiting console input. It could be in a wait. It could be waiting on a pipe and so on. So what do we do? Well, first off, we want to wake it up. And that's easy enough. Just change it from sleeping to runnable. We want it to go away right away. Except it might not be too clean. Okay? Maybe, for instance, we're in the midst of creating a file. So we were in a system call for creating a file, and it had gone to sleep as part of that because it had to write to the disk. And if we just kill it right now, it doesn't finish the creation of the file. So we should either finish the creation of the file or back up and have nothing, but we shouldn't leave it in an inconsistent state. So for some cases, we can't quit right now. Some of the sleep locks check for killed. An example would be, we're writing in a pipe. We check to see, is our buffer full? And if it's full, we'll sleep. But before we sleep, just check and make sure, is the reader still there, right? Or is there any readers there? And also, have we been killed? Because if we're killed, let's just bail out of here. Similarly, for pipe read, if we've been killed, we just exit right away. But if we're in the middle of read-write to the disk, then we don't do that. So we don't check to see whether they've been killed, because it's important that we complete this operation, because otherwise we may be leaving the disk in an inconsistent state. So it may be that it's going to have to just finish off whatever it was doing as far as, let's say, a open system call. And when it finally is done, it'll return from system call, and here, right after the system call, we check and see, oh, are you killed? Okay, so this is sort of our fail-safe. So the idea is, let's say the target, the thing to be killed, the process is in user mode. Okay. That is, it's executing user code. Does it die immediately? It does not die immediately. Instead, it can only die in the kernel. So if I am a Lazarus type process, can I just make sure to never make kernel calls? I'll still get preempted, right? The timer will still happen. I'll go into the kernel, and at that point, then we will note that it's killed and actually exit it.
What is it actually running for in order to be killed? Or running in order to be killed?
It doesn't. That's just one possibility, right? Well, there is cleanup code that needs to happen in the context of the process, like finding its children and so on. And so it's easier to go ahead and let that process do it in the kernel. So we need to be running on behalf of the process in the kernel. Okay. So next system call or timer. If we're in the kernel, we're not going to ever go back to user mode. All right? So if we were in a timer interrupt, we're done. We're just never going to go back. If we're in a system call, then we're going to be checking to see whether we're killed and call exit. But again, we may spend a while in there. Right? We may spend a while because we may need to be completing lengthy operations.
Are there any protections from like a process opening a file on disk and then leaving that open and then doing other stuff to prevent itself from ever being killed?
So having an open file is not enough to keep you from being killed. So if you have open files, the kernel will be happy to close them for you on its way of kicking you out. So it's really the duration of a single system call that can be a problem, okay, where it may have to finish that system call. Finish in the kernel, not ever get back to you in the user mode. So JOS, how does it deal with these problems? Remember we talked about the lost wake-up problem, and the JOS deals with it really simply. We don't have any interrupts in the kernel, and so therefore we don't have this potential problem of we have our while loop for our sleep, and it may be between the time we check our condition and we call sleep the wake up happened. Can't be. Yeah.
Is it like, are interrupts disabled in the kernel just like whenever you're executing kernel code, or is it like the big lock that disables, that we implemented in this lab, that disables?
So is your question, are they explicitly disabled, or does it happen because of the lock?
Yeah.
I don't know. I don't know. No, I take it back. I think I do know. So I'll have to think about that more. So this idea of terminating while blocking is kind of simple because JOS doesn't really have any lengthy system calls. So that kind of makes life easier. So the fact that a system call may have to complete is not really much of an issue. There's no file system, there's no disk driver in the kernel, so there's none of these lengthy operations here. Those are in user space.
So last time with the lost wake-up call, we saw that the sleep function had to take in the lock as a parameter so that we didn't have that issue.
We don't have to do that. That's a good point. We don't have to provide the lock as part of the sleep or the wake up. Yep. Okay. All right. So today, and I don't know if you guys look at the schedule ahead of time much, but what I decided as I was going over this is we really need 2 lectures for the file system. And so today and Wednesday are going to be file system. I've pushed out what was going to be on Wednesday to next week. So, what's a file? And any particular system may slightly tweak this definition, but let's say it's just a named collection of related information stored in secondary storage. It's like the smallest piece that you can create in this secondary or long-term storage. Key thing about long-term storage is it stays. It stays around, right? You shut down your computer and your files are still there. Okay. So this idea of secondary storage actually is not strictly necessary. So I can think of an example. Anyone heard of or seen a Palm Pilot? Okay, it was one of the first handhelds. It was like a $100 little device like this, and you had a stylus, and you wrote a special alphabet in, and it was actually really good as an organizer. Okay, they had no secondary storage. All they had was dynamic RAM. Yet they still had this idea of stuff that was there, and when you quit your application and came back, it was still there. And when you powered down your device by pressing the power switch, it was still there. How?
Maybe send it to somewhere over the network and then re-download it.
Oh my goodness, you're imagining a lot of infrastructure, especially back in the 90s.
Fair.
So the Palm Pilot ran on 1 AAA battery. It would last for a month, so fairly low power. And so that's how it worked. This basically would provide power to the dynamic RAM. Okay, so that was still there.
So it never.
What about when you need to change the batteries?
What about when you need to change the batteries? That's a good question. Well, it backs up over the... Oh, wait, we don't have that infrastructure.
Only change one.
How quickly would you need to go? But seriously, what if I gave you a time budget of we're going to require the user to do it within 60 seconds?
Well, if you make the device cold enough and you have enough error correction.
Say that again? Yeah, capacitor, supercapacitor is what they had there basically. So that you had enough time to replace the AAA battery. Okay. So anyway, these are ways in which you can do stuff without actually secondary storage. I waited a long time. They do line up, nice. All right, so typical file systems are sort of Unix, Windows, Mac OS model, hierarchical namespace. Original MS-DOS did not have a hierarchical namespace. It had on floppy drives just flat namespace. So you had files and there were no directories. But these days we have hierarchy. Create, open, close, read, write, seek, all are fairly standard. And a file is a single collection of bytes. Now you might say, what else would a file be? Well, it turns out people have done lots of different things. For example, a file is a database. So the Apple Newton, which predated slightly the Palm Pilot, and was famous for having handwriting recognition that wasn't so good. The B operating system as well, which Apple almost bought instead of Next OS. In both of those, you have databases, okay, where you can index by databases. You have indexes on keys in those databases, and you could look stuff up. Find all records where age is greater than 19, or age is greater than 19, and height is greater than 6 foot, sorted, descending by such and such. Right? So typical database type stuff. Or files as just an array of data chunks. This is like the Palm OS. So what it had basically was, a memory chunk here, and a memory chunk here, and we'll call this one record number 1 and this one record number 2. We'll define what's in them. They're all in memory because there was no place else besides memory, so it was very easy and quick to deal with these. And you keep track of, has this been modified or not? There's a unique ID for each one. It could actually sync back to a desktop and use this unique IDs to only move the modified items. Other possibilities, not just a sequence of bytes. So VAX VMS. Text files were not a sequence of bytes. They were a sequence of lines of text. So you could get particular lines in the file. And the line terminators, you sort of didn't have to know about, right? The fact that it was a \n, or that on DOS it's \r/\n. And then there were also binary files. So when you created a file, you have to say, is it a binary file or is it a text file? Files with more than one chunk of data in them. So what I said was, we have a single collection of bytes. So this is really multiple collections, multiple sequences of bytes. The Mac was the most famous one of these, I guess. So the Mac OS from day one had your data. So you might have, for example, a text file with your data in it. And then also had a separate, what was called a fork for the file. So the file actually had data fork and the resource fork.
What goes in the resource fork?
So if this file were an application, the data would be the code and the resource would be the resources. Like, I have a dialogue and this describes the dialogue and the text in the dialogue and so on. And so with a resource editor, a translator could go in, for example, and open an application and change just the resource fork and translate it that way. So change the English text into German, relay out where the buttons are because they need to be larger in German because the text is bigger and so on. Yeah.
So it's kind of like the resource file is like metadata about the file, or?
It's not metadata normally. It is additional information. So another example would be files could have custom icons. That was stored in the resource fork of the file. So you could have a text file with a picture of Bugs Bunny when you're in the Finder, and that picture of Bugs Bunny would be in this resource fork.
Does that have anything to do, like, with, I know on Mac OS, like in your folder, you'll have a hidden file where it's like DS?
It is a lot like that hidden file. Have you ever seen an application, a Mac OS, a .app, if you go look at it in the Finder, and there's actually a whole hierarchy of stuff under there, but it looks like just one thing in the Finder? Same kind of idea, although that is really a figment of the Finder's imagination.
Mm-hmm.
This was actually part of the file.
Okay.
So it was very complicated, though. If you wanted to transfer a file from one machine to like a Unix machine, it's like, well, there's actually two parts to the file, and like the Unix machine is going, what are you saying, two parts to the file? So.
Then what do you actually put in the data? Like if you're putting things that kind of seem like data in the resource?
So this resource was a little mini database in some ways, and some people would abuse it. So I think that there was a tech note from Apple: the resource manager is not a database, okay? Because people would try and put a lot of stuff here, and it had poor performance. So it was normally extra stuff, and I don't know how to describe extra stuff any better than that, but it was extra stuff. Oh, I'll give you an example. That was as well as an icon. Let's say you printed a file, and you chose some settings for how you wanted to print the file. You know, you wanted 2-up, and you wanted a watermark on it or something else. That configuration information for printing was actually normally saved in the resource fork along with your data. So when you went to print that file the next time, it would use the same settings. So that's one possibility. Did you ask about metadata?
Yeah.
Yeah, so we do have metadata, and we need to talk about metadata. But first, let's erase this. Yeah, getting to be good at this. So metadata is not the data in the file, right? So we have here it's called the file contents. But everything outside of that we might want to know about the file. What's its name? Who owns it? What permissions are there for it? When was it created? When was it last modified? When it was last opened for read? How big can it be? Is it locked or hidden so it doesn't show up in the Finder, let's say? Is there an icon associated with it? Type and creator, this is not that common, but this was on Mac OS. So you could have the type would be what kind of type it is. So this might be text. And the creator was who owns it. So I could have different text files owned by different creators. I might have one .c file that I want to open up in Visual Studio and another .c file that I want to open up in Eclipse, let's say. And so you could have the same suffix, the same type, but a different application creator could do that. So we need to make sure we have a way of saving this metadata as we're dealing with file systems. Okay? 4 file types. 3 basic ways people have done this. File extensions, right? The most common, it's been around for a long, long time. And the idea is if we see a .doc file, that's going to be a Microsoft Word or .docx, right? Microsoft Word. And so if we see, so we will set up some mapping from an extension to an application. In some cases, it could be enforced by the OS in some ways, or on Unix, for instance, it's just a convention. Okay, it's a convention that many applications require. So for instance, your C compiler, if you pass in a foo.o, will it look in there for C code and compile it? No, it'll think that's an object file. So it thinks .c is a C file. What does it think is a C++ file? What? CPP or? CXX or CC or C++ probably. All those probably accept. Or possibly capital C. So magic numbers. That's one way to identify what kind of a file is. So if you have, especially for binary files, you want someone knowing, I mean, I have this file, I wonder what it is, right? I don't even necessarily have an extension. Well, we know, remember ELF. Remember we looked at our ELF file to make sure that the magic number matched? And the rule says, at the very beginning of the ELF file, you're supposed to have hexadecimal 7FELF. I think it's actually, I think it's actually backwards. I think the F and the L and the E and the 7F are in the other order. So this is the big Indian, little Indian problem. How many people are familiar with big Indian, little Indian? Your hand. Okay, good. How many people know the story of where the name comes from? More than I would expect. All right. So the big Indian is, let's say we've got the hex value 1, 2, 3, 4. How is that actually stored? 1, 2, 3, 4. Yeah, let's just do 1, 2, 3, 4. So we have 2 bytes, the 1, 2 byte and the 3, 4 byte. How does that get stored in memory? Right, so this is 0, this goes down. One possibility is it's 1, 2, 3, 4, and the other possibility is it's 3, 4, 1, 2. So the first byte you see in memory might be the top byte, or it might be the bottom byte. And one can come up with some rationalizations of why one is better than the other. Okay? But the fact is, some countries they drive on the left, and some countries they drive on the right. So this, for instance, is x86. This is, I don't know, Motorola 68000, the original Mac, or the Palm Pilot. ARM can do either one. So you have a mode where you can switch it in one or the other. But the fact is, since most stuff is Little Indian, peripherals are designed to work with Little Indian, and people don't really test it quite as much to see whether it works in Big Indian. So. All right. And so anyway, the reason we get Little Indian and Big Indian, and it's not Indian like someone from India, it's Endian. And because of which end we read from here? No. From Gulliver's Travels, of course. Right? Gulliver's Travels, Gulliver traveled to an island, and there was this civil war going on between the people who took their soft-boiled eggs and opened the big end or the little end. So this is pointless religious wars, basically, which we're good at in the computer field. So there are pointless ones like spaces versus tabs, right? And then not so pointless ones like Emacs versus Vim. Right? So, well, because there are real reasons there. There are a lot of differences. Not so much difference as spaces versus tabs. All right. And let me just show you. So if you man magic, it turns out there's a big database of magic numbers. And it tells you what all is in there. So user share. Okay, so this is, let's look at, what was the one we wanted to look at? ELF. And we've got this very complicated thing in here, which talks about, so it can actually be fairly precise about what kind of an ELF file it is. And there's a bunch of stuff. Is it a 68000? Is it an Intel 8486? And somewhere in here, we actually have the information somewhere there. At offset 0, there's a string 177 ELLF. Okay. It's a string, so this is the order it's in.
Which means if you read it on a Little Indian machine, it will be backwards.
All right, and we can see here LE long. Guess what LE stands for? Little Indian, right? So. Or file types on the Mac were stored as a file type, so you could actually have the name be whatever you wanted. Extension was irrelevant. And that's a used to be thing. Okay, links. Sometimes you want more than one name for something. Or you want to store it one place and another place. There are two basic approaches. So if we've got a file foo here, so this is foo contents. So its name is foo, and it has some other attributes as well. Well, we can have I have to redo this because my example points to bar. So we have bar, and this is the bar contents. And then we can have a file foo, which is basically a pointer to bar. Okay? That works. Those are called symbolic links in Unix, aliases on the Mac, shortcuts, I think, on Windows. The problem is, what happens if bar goes away? Okay? Or bar gets moved. On the Mac, actually, there's a lot of machinery to make sure even if this gets moved, it still finds it. But if you delete this, bar foo still looks like it's there, but when you try and use it, it doesn't work anymore. Okay. The other possibility is you have the contents, so these are the file contents, and you have foo that is this file, and bar that is this file. And as long as either one of them is there, if one is deleted, the other still has access to it. And these could even be in different directories. Okay? They've got to be on the same disk drive because we're sharing one copy of this. It requires some machinery because that means the last time you remove a link to a file, that's when you can actually delete the contents. But as long as there's at least one link, you have to maintain it. So part of the metadata is how many links do I have? And if you're removing a link, if it's now going to 0, then you actually free it up.
So foo and bar are supposed to be representing two different files, but they contain the same contents or something? Okay, and then the first one is just, okay.
Yep. So to give you an example, let's say, so let's go over to Knuth. So we can see here, this is in the bin directory of CS134, that i386 elf strip actually is a symbolic link to a subdirectory in here with this long path where it actually is. Okay. If this is no longer there, the link doesn't work anymore. But while it is there, it does work. So part of what it provides is shorthand.
What's the point of having symbolic links then? Why not just always do code links?
You can't cross file systems for one thing? So
That's a good point. So a symbolic, that's a great reason. So a symbolic link can point anywhere, including to some other drive, whereas hard links have to be on the same drive. Yeah, that's one good reason.
I was just going to say, like, I feel like I always use symbolic links. I use a lot of symbolic links, and they have important documentary value. Like, in the bin directory, you have all these links that are pointing over to this other place. But if you had hard links, it would just be, well, it looks like there's a bunch of binaries here, and you have no clue.
Yeah, that's true. There's no way to find the relationship between this is the same file as this one over here, I mean, without a ton of work and iterating through everything. Okay. File namespace, one level. This is just flat. We don't see this much. 2 levels, one per user, you don't see very often. This is commonly what we use. So we have this hierarchy where we might have, for instance, slash and bin and user, and within bin we might have vim as a file, and with the user we might have, Rhodes as a directory and more stuff. So nothing. Should be nothing surprising. For files, we want to be able to open, close, read, write, seek. We also need to be able to create files and to delete files. And we're going to need some permissions. So open, close, read, write, and open and close, we'll need we don't need any permissions for open. Close, sorry, we don't need any permissions for close. Open. We'll normally need permissions, right? So at that point, it'll check permissions and say, do you have permissions to open this file? Once you have it open, you can do with it almost what you will. If you open it for reading, you can't write. But other than that, that's fine. Creating and deleting, you're going to need permissions. But it's normally you're going to need permissions on the directory that you're trying to create in, or the directory that you're trying to remove from. Okay? It's not an attribute of the file itself that you have permission to delete it. It's an attribute of where it's located that you have permission to delete it. Getting and setting attributes also may require permissions. Somewhat less common, like appending. So in the case of Unix, if you want to append, there is a flag you pass to open to append. XV6 doesn't support append, although I think that's one of the exercises in the book that it says that you could do. Rename allows you to rename a file, and that's sometimes provided and sometimes not provided. So in fact, there's no rename in Unix. So how do we rename? What's that? Okay, so move is, here's the question. What system calls is move going to be making, right? It's just a user program. So when I say move A to B,
you could create a hard link and then delete the original.
it's exactly what's done. So you basically link, I'm going to just put in here A and B, and then unlink, which means remove A. That's what's done. And that's why move complains if you try to move stuff from one file system to another file system on another drive, because this whole link unlink thing doesn't work because you can't link across drives. For directories, you need to be able to create directories, delete directories. Again, those permissions are probably based on the directory it's part of. Open a directory, close a directory, read a directory. In Unix, it turns out these don't exist. So in Unix, these don't exist. And actually, delete doesn't exist either. Guess what you use to delete a directory? Unlink. So this is in Unix. Yeah.
So if link and unlink is for hard links, then how would you do symbolic?
If you want to make a symbolic link, there is a different call that you're going to use to do that. Yeah, you would have to use.
And so with a symbolic link, if you delete something and then that thing no longer like points to it and try to access it, it'll just like
You get an error when you try and do an open. So the open system call will fail. There's an error. There are two different errors. One is like the symbol. Let's just see what it is.
so it doesn't if there is a symbolic link and you delete whatever it's pointing to, it doesn't also delete that thing, like the I don't know.
If you delete a symbolic link, it'll delete the link to it and not the original.
So why doesn't it? Oh, okay, got it.
Yeah. So if we look at somewhere here, there's going to be a symbolic link, let's say. Okay, so eno entry is what you're going to get. No such file is what you're going to get if either the file's not there or you have a symbolic link and the thing it's pointing to is not there. Can you have a symbolic link that points to a symbolic link that points to a symbolic link? Yes, you can. However, you can't do too much of that. So let's see. Too many levels of symbolic links. And you have kind of a loop. It used to be 8, I think. So. But it figures at some point something just seems horribly wrong. And it doesn't actually check to see that there's an actual loop. It's just, I've gone too far. Okay, so let's talk about the disk. We will talk more about disk on Thursday, but for now, let's just look at the disk as a simple sequential sequence of equal-sized blocks. Right? How big are these blocks? Equal size, that's right. 512 bytes, 1K, 2K, 4K, those are all possibilities. Okay? It's going to, at the lowest level, it depends on the disk controller and the disk. They'll tell you how big the blocks are. So we can read a block and we can write a block. That is, for now, as we're implementing our file system, what we're going to look at. So if we talk about block number, it's just a location on the disk. We talked about file metadata. There's also file system metadata. So if this is my file system, And I've got, let's say, file 1 contents and file 2 contents. This is conceptually, because we don't actually put them like this on the disk. And file 3 contents. Everything else we're going to call the metadata. So all the green stuff is metadata. All right, so part of the file system metadata, we're saying by this definition, is the file metadata, right? The names of files, the permissions of files, and so on, is part of the metadata. There's still metadata if you ignore all of the metadata for each of the files. Like, I'll give you some example, which blocks are free and which are in use. So this is file 2. Which blocks contain file 2's contents? And, importantly, in what order? Okay. And the what order matters, of course, right? It's not very useful to have a bunch of blocks not having the right order. Speaking of which, I always wanted to have, how many people have used the sort command for Unix? Right, a lot. If you ever look, there's a lot of options to it. You know, sort minus this, sort minus that, sort numeric, sort string, and so on. I always thought it'd be interesting to have a minus b, sort bitwise. Okay, it's a great compression technique. So I give you a 1 meg file, and it puts all the zeros at the front and the ones at the end. Anyway, so the order matters, is what I'm saying. The order of bits matters. We need to keep track about open files. So this is going to be in memory. All right, while our machine is off, right, if we've shut it down, we don't need to know what files are open because there are no open files. And we normally don't need to keep track on the disk of what the files are open. So just in memory. So we contain basically a file table for the system. And this has got to have information like what are the attributes for the file, where are the disk blocks is a very important part. Where are we within the file, right? If we read 10 bytes, then we're 10 bytes into the file. And when we start reading from there, we're going to start at 10. Access mode is this readable, writable. Reference count, what would the reference count be? And Nandika.
The number of links, hyperlinks to.
So that is a good possibility, but that's not what I'm thinking of there. So we have a link count too. And I'll give you a hint.
The number of processes that are using that entry in the file.
Exactly. The number of processes that are using this file. Because we don't actually want to close it until all of the references go away. And we might have the same file represented more than once here, right? Because we might have opened the file, even in one process, we might open it read-only and read-write. We're allowed to have 2 file descriptors that refer to that, right? And so we would have different entries in the open file table. They'd be sharing, of course, some information, like the disk block locations and so on, but some of the information might not be shared, like current location within the file. And then per process, we have an open file table, which just refers back to the system information, right? So we might have, let's say, proc1 that has file descriptor 0 that is a reference to this open file. And then we might have proc2 that has file descriptor 1 that is also a reference to this file. The only way we could have 2 different processes sharing this, in fact, how could we get that? How could we have 2 processes sharing the same?
Well, one of them opens and then it forks.
Yeah, there's got to be somewhere, there has to be a common parent of these two that did the open and that they inherited it then. How did this guy get to be 1 instead of 0? This guy's 0, this guy's 1? Yeah, would have had to do a dupe and then a close of the 0. All right, we want to find the blocks of a file. Okay, we've got a file. Where is it? How are we going to lay out? Right, we know we've got this from 0 to n minus 1. Where's our file going to go? So we have our blocks from 0 to n minus 1. And what you could do is say, well, if I have a file, I'll put it right here. I'll put it from blocks 5 to 37. I guess n is not very big. So this is file 1 contents. There are good things about this. If you go to read this file and you read sequential blocks, 5, 6, 7, all the way to 37, it's extremely fast. As we'll talk about when we talk about the hardware of disks, you don't have to seek. Right? You can just read, and your throughput can be very high. A big downside, though, is this kind of similar to when we were fitting processes into memory, right? How big is this going to be? If we knew exactly how big it was, then yeah, this would be great to make it contiguous. How many of you have used a disk defragmenter ever? All right, so what it does basically is it takes all your files that are all spread out and it moves all of the data around so that all of the blocks of a file are contiguous, so that theoretically it's faster to be able to access. In some cases, you know the files are never going to change. Like if you have a CD-ROM, it's very hard to change those files, right? And so there, it makes some sense to sort of pre-figure out, we know how big each file is going to be, and we just put them all so that the contents are all sequential. Does that make sense? But in general, if you wanted to do this, when you create a file, you have to know how big it is at the time you create it, right? You do the first create. You can use a linked list. So, and we have the potential for external fragmentation here. So you can do a linked list where you have, let's say, file block 0 contains a number, I don't know, at the end of the block that's 4. And that says, okay, the next file, the next block in this file is at location 4. And then the next one is at location 0. And the final one is, let's say, -1. So that's how the pointers are represented. Problems with this are a couple. One, your blocks now can't use this, however many bytes this is. So your blocks are now somewhat less than a power of 2, which this is a little weird. There's nothing inherently wrong with it, but it's a little weird. And in order to get to block n of the file, you have to hit the disk separately, right, to find out where it is. So if you want to just seek to this location, you've still got to hit every intervening file. Whereas here, if you want to seek to a particular location, you just calculate. I know where the beginning is. I know how big the blocks are. I can go there. Does that make sense? Questions? Okay. What you could do is do an external linked list. So you could have a map, basically, that tells you that the first block of the file is 4, which is this guy, right? And then the next one is 0, and the next one is 3, and then there's no more. So if you kept this on the disk, let's say, but then also read it into memory, then you could, within memory, so just read this data structure, and then from then on, it's order 1 access to any offset, any block. Okay. You have to keep this in memory. It does take a little amount of some space. The extents idea says, rather than keeping everything contiguous, allocate chunks of contiguous things. So you might have a start and however many blocks there is, and then another start and however many blocks, and you kind of keep those linked together.
why do you have to load it into memory in order to have over one access?
Because if you have to read this from disk, well,
Oh, I see what you're saying.
depending on how big this is, right, this may take you many accesses to read. Okay. What's often done, where do we go here? Sure looks like I have a duplicated, I have a duplicated slide. Here's what Unix does. So Unix says, all right, and let me back that up. Here's what the original file system for Unix did in v6. And xv6 does something fairly similar. And if we look at modern file systems like, I don't know, ext3 for Linux or something, they're still based on this idea. So it wouldn't be totally weird. So the idea is every file is going to have a data structure called an inode associated with it. And that inode is going to store the location of the disk blocks. Okay? So this fits in a disk block. And what we're going to keep is block numbers. So this might be 35 and 172 and 56. And let's say that's all there is in this. In this case, this file is 3 blocks big. Okay? We will keep, so this points to a block here. So this is, so we'll call this file. How do I want to? I'm going to call this file 1.1. So it's file 1, and it's block 1. And 172, let's say, is file 1, block 2, and here is file 1, block 3. Right? So we read this inode into memory, and then we can have direct access to here. How big a file can we have with this approach? If this is 512, and each of these is, let's say, for the argument, 4 bytes, how many blocks can we reference? 128, sounds good. So we can have 128 blocks in our file, which is not very big if a block is 512, right? So that'll be 64K, which, yeah, 64K, which is not that big as files go, right? So, but the nice thing is you can get at these things. You have the inode in memory, so you had to read that into memory, and from there you have one access to get to these. But what they do is they reserve here at the end a level of indirection. They say, okay, here, this is going to point to, just as always, a disk block. So this might be, 66. But instead of being a disk block with contents of your file, it has a level of indirection. And so it has itself pointers to disk block. So this would be file, these are the first 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then we get an indirect one. So this is going to be number 11. And this will be 12 and 13 and all the way, and this will be F1, 11 plus 128. We'll say 11 plus 128. 139. Yeah.
Is there a reason that's not the last block?
Yes, because now we've just basically doubled how much we can have. So instead of 64K, now we're at 128K files.
Yeah, but you could have, you just as easily have the pointer be the last, like fill up the whole thing until the last one.
Yeah. The problem is 128K isn't big enough. So therefore, let's go ahead and make this one be, we'll use a different color for this, 99. And this one will point to a disk block. All right? That points to disk blocks that themselves point to, I suppose if I'd done my color, I would have, I'm going to change my coloring right now. This is a green color. And this is a green color because it's actual parts of the file. And then these are going to point to green blocks as well. And these are going to point to green blocks. And these are going to point to green blocks. And then, wait, we still have one left? I know. Let us make a triple indirect. That then points to. Does that make sense? So we can store a lot, right? Sort of like our 2-level page tables, except maybe we got a 3-level pointer here. So here we can store 10 blocks. Here we can store 128 blocks. Here we can store 128 squared blocks. And here we can store 128 cubed blocks. And if we needed to, move these up one and add a 4-level indirect level.
How do you decide, like, which ones you put where?
You're always using, so as the file gets bigger and bigger, you're having to spill over into single level and 3-level. So small files are quick to get to access, right? Because you only have this one disk access to get to them. Does that make sense? And in fact, I think your job for Wednesday, your homework, is to add, I don't remember whether there's one level, I think there's one level injection right now in XV6, and yours is to add a second level. Okay, we're not doing 3-level. Go ahead, YT.
Slide it says 256, and you were saying 128. Is that?
Oh, it's because we have 1024 byte blocks. I was thinking 512 byte blocks.
Okay. So for XV6 it's 512. Like
I don't remember. You would. It's a constant. You just make it a constant.
So
Yeah.
it depends on like your system.
Yeah. Depends on your system.
The properties of the physical disk. Some disks will have 512 byte blocks. Some will have bigger blocks.
Beyond that as well, even though you might have a disk with 512 blocks, you might choose to treat it as having 1024 byte blocks and just always write 2 at a time and read 2 at a time. That's not uncommon.
Interrupted halfway through a write. Halfway through writing a double block.
Well,
It's half written and half
yeah.
not.
So normally what you could do is you can send multiple commands to devices. It's actually fairly interesting, right? So devices have RAM on them to store this set of stuff that should be written. So when you write to a drive, it might not have actually written. So what happens if you turn off the power? After you issue the write, and it says it's done, but it's still just in memory on the hard drive.
We'll hopefully have some backup power.
There is backup power in the form of a, what do you call it? It's not a gyroscope, it's a...
Oh, it's spinning.
It's spinning. And so they actually ensure that there's enough rotational energy that they can keep powering to do the writing that they have promised to do. Okay, which is kind of cool. All right. Free space. This is the question. I've got this big disk. I've got a bunch of blocks. Some of them in use, some are not in use. I need to go do an open, let's say, or a create, or I'm making a file bigger, and so I need to allocate a disk block. Where do I allocate? We could use a free list, a linked list, but that's kind of a pain, and we have to go to disk. Commonly what's happened, a bitmap. So we just have 1 bit per block. Okay, so the first bit tells you about block 0, and the next bit tells you about block 1, and the next bit tells you about block 2, and you do a little bit of bit shifting arithmetic, and you can then find out whether a block is in use or not. So it's quick, to find out whether a block is in use, and it's quick to mark a block as in use. This bitmap, you better store on disk too, right? Because when you start up your computer, you don't want to run through the whole disk finding what blocks are in use or not use. So you want to save this to disk. So I guess checking if a disk block is in use is very quick. Setting it to be in use is a little more expensive because it's going to write it back to the disk. If you have a 16 gigabyte disk and 1 kilobyte blocks, then that's 2 to the 24 bits you need to keep track of, right, for each of the 16 megabytes, so 16 megabytes of disk block numbers. So I can distinguish each of the 16 meg of disk block numbers, the 224 bits, and so that will, if I put them in bytes, be 2 to the 24. So it's about 2 meg. So for 16 gig, that's not so bad. Actually, I'm sorry, finding a free block can be expensive if it's mostly full. If you're searching through to find a 0 and you're finding lots and lots of 1s, that could be a slow process. All right. This is the last thing we'll do today, and this is, I think, very interesting. So here's how directories work pretty much in all Unixes, certainly classic Unix. NXV6 works this way. So we have a directory is just a file with fixed size structures in it. We've got the name, we've got attributes, and we've got an inode number. Okay? That tells us. Then there must be some attribute here that says whether this is in use or not, because you have to know how many of these are actually valid, because you've got an entire let me just think about this a second. No, so a directory is a file. That's what we're saying here. So the size of this is not a multiple of the block size. It's however big we've made it. Let me just look at an example, and let's look at cat slash. I know it's a directory. I'm okay with that. Cat less than slash. You're too tricky for me. Let's see.
Sometimes you can do them, like it'll show us stuff. It'll say it's a directory.
Yeah, there we go. So
I think that's just a no, that's not C.
That's
That's not the actual directory.
well, it's interesting because we've got these applications. Okay, so all right, maybe we can no longer do that. Since it knows it's a directory, it doesn't look. So anyway, we're going to have all these. We look, for instance, at a directory. So here's a directory. Here's slash. Okay, slash has some attributes associated with it and has a list of disk blocks associated with it. Slash doesn't have very much stuff in it, so it just has one disk block associated with it. So if we look at a disk block, this is the actual contents of the file. Okay, so this is the contents of slash. And so we've got 4 entries in it. User, which is at this inode. Dev, which is at this inode. Dot, which refers back to 2, and dot dot, which refers back to 2. You know when you do a cd dot dot, the shell doesn't know anything about dot dot. Okay? You'd think it might, but it doesn't. All the shell does is say, well, change directories to dot dot. So it goes, looks in the current directory, says dot dot, points to somewhere else. That's where it goes. Okay? So dot dot is actually a file in the current directory. And dot is a file in the current directory that points back to itself. So every directory has a dot and a dot dot. Dot points to itself, dot dot points to its parent, except the special case of slash, where dot dot of slash is slash. So we're trying to do user include standard IO. We go to user, that goes in here. That says our inode is 36. We go to this inode. It says first block. We're now going, let's see. 83 takes us to here. This is the contents again of include. And this is the contents of user. This is the contents of include. And now finally we can figure out what is the block for standard IO.h. Does that make sense? So the inodes include, again, these list of block numbers and possibly single and double and triple indirect blocks. Yes?
Do these blocks contain a mapping from like contents to an inode? Because it seems like we're going back to the inode.
We always go to the inode because files are represented with inodes. So user is a file. We go to the inode, and the inode tells us where the contents of that file is. Okay? And then within this file, contents, we're going to have a reference to another directory or file, and so on. And if we look at standard IO.h, that's going to go to another inode. So we have inodes, and we have blocks. An inode's one block.
And when you showed like the single redirect,
Yep.
The block could go from like F111 to F111.
Plus 128. Yeah.
But why does the original inode go up to
Oh,
12 or something?
we store some. Yeah. It seems like it should be 128.
Yeah.
We store extra stuff in here.
Oh, okay, it's just
Yeah. Yeah. There's last access time, last modify time, some other information in here. Metadata, yes.
These inodes themselves are stored inside disk.
They're on the disk as well. So we have some of the disk is we're storing inodes, some of the disk we're storing. Yeah. And we have to know things like we have to know where slash is. So we have to know which inode contains slash. All right, so see you on Wednesday.